Good morning, everyone. So first, today we're going to work quickly on the canonical quantization. So it seems that most of you are quite familiar with that, but I still want to take the time to go through again and maybe from a different perspective that the way you learn it in undergraduate, just because, as I mentioned yesterday, I really consider that this is a kind of minimal background I really want you to have. And anyway, I'm going to use that to introduce the path integral formalism. Okay, so I just want that everyone is on the same page to make sure it's also a way where we're going to introduce some mathematical objects like the notion of Hilbert space and this kind of thing. So these are really important notions that I really want everyone to have. So I will do a short intro, then we're going to start from the classical mechanics and try to go from classical to quantum. And then, yes, one step is missing here. That would be like more. And in fact, we will see that if we choose a right formulation of classical mechanics, and if coming from experience we can make a few changes in the postulate, then we can really go to the quantum with and end up to the postulate that you had in your tutorial yesterday. So we're going to go back to those. And then I just want to show that using matrix representation, you can solve Heisenberg equation. And then the question will be, is it the end of the story? Are we solving, what does it mean to solve a quantum problem, okay, at this stage? And we will see that, in fact, something is missing, is that usually what you want, it's kind of number prediction, because you want to compare with what you're going to measure, okay? And of course, at this, when you solve using matrix representation and Heisenberg equation, you're going to end up with matrices. So the question will be how to go from here to here. And then we're going to finish on the abstract structure behind everything, which is the Hilbert space, okay? So let's maybe start with a short game. So let's imagine that you're a physicist at the end of the 19th century. And at the end of the 19th century, you would already know that the Planck constant would play a fundamental role in the quantum mechanics laws. You would also know that since quantum mechanics is going to reproduce all the successes of classical mechanics, you still expect that it has strong similarities with classical mechanics. And so what could be, if you were one of these physicists, so you know that the classical law of physics should be changed, that you should include the Planck constant. If you were one of these physicists, what would be your strategy to guess the quantum mechanics laws? Okay, so you could start with Newton's law, because it's usually what physicists were using at the end of the. And the question is, so this is classical, now how do you go to quantum? And quantum, you know that it still should be, for at the end of the 19th century, you still expect that it's similar to classical, but you want to introduce this new constant. So what would be your suggestion? So maybe to start, what are the units of this constant? This is something quite important to have in mind. Yeah, so and this is the unit of an action, okay? And you know that this constant is indeed called the quantum of action. So if I wrote that, so energy would be, you need a mass unit, then you would need length square, and then it's going to be time minus 1 times time, so minus 2, so it's minus 1. So this would be the unit of this constant. Okay, so now if you compare to, so for example, if your suggestion is to say, okay, so let's go to quantum, saying that now I'm going to write something like this. Okay, so directly, this is a kind of, okay, I'm going to add H as a kind of perturbation to my Newton's law. And directly you can see that this is not possible just because of unit issue, okay? So what are the units here? you have a mass, and then this is an acceleration. So you get okay, so what would be if now we remove this unit? What else could we try? Let's try to factorize maybe by MA and try to get something. So using, for example, X and P, something without unit, X, P, and H. So what are the options to get something without unit using H, X, and P? What can I add here?
X times P.
So X times P. Yeah. Okay, yeah, really good. So this is without any dimension. But so what is the issue with that? You see that even in everyday life, this kind of term will be already quite large. So this is not really compatible with experiments. I mean, at the end of the 19th century, physicists just discovered that maybe classical mechanics was not complete. We need to reconsider and talk about quantum mechanics. So this option would not work either, okay? It would mean that quantum effect would be really visible in everyday life. But since we have found that this is the same, we could also try this kind of thing. And again, the issue now is that, of course, when this becomes small, then this number becomes really huge. So again, this would mean that quantum effect would be really important, okay? And in fact, starting from Newton's law, indeed, there is no way to go to quantum mechanics directly, okay? This has been tried. And the first formulation of quantum mechanics, so Heisenberg and Schrödinger's formulation, are in fact very far from classical mechanics. So how can we start anyway from classical formulation of classical mechanics to go to quantum? So I guess you know the answer because first I wrote the title here. So we're going to use, of course, Hamiltonian formalism. And this is to keep in mind. So this is something really important. And I think Rob's tried to emphasize on his talk about that yesterday, is that so classical mechanics at the end of the 19th century really think that could explain everything if you add electromagnetism, okay? Almost before discovery of this of these quantum effects. But the point is that this is not the more abstract formulation of classical mechanics, okay? If you go to a higher level of abstraction, then you go to Hamiltonian or Lagrangian formalism. And you could think, oh, this Hamiltonian or Lagrangian formalism doesn't bring so much to the theory, okay? It's still the same theory. But you really see that the fact that you're able to get something to a higher abstract level then allow you, as was mentioning Rob's yesterday, then to ask new questions and even to then expand the formalism, okay? To answer new questions and to have new questions. So this is something that is going to come back several times. And I think this was also, I don't know what is that. This was also the point of, Rob's yesterday, is that now there are still open questions in quantum mechanics. Like, for example, quantum gravity is one of the main questions. And I think his point with the introduction of the causal quantum mechanics, but maybe that the way we think about quantum mechanics is not abstract enough or is not general enough to answer the kind of question we would answer if we talk about quantum, if we want to go to quantum gravity, okay? So let's now start from, so this was just a short intro. So now I just want to review very quickly the Hamiltonian formalism and really here on what it's going to be like a few minutes. It's going to be really quick because I know that you're all familiar with that and you had a really great lecture on it by David during the front end. But the question is, as I said, we want to start to classical mechanics and to see how we go to quantum mechanics, okay? Okay, so what is the starting point of Hamiltonian formalism? So no, I guess, any question now? Or? Okay, so what is the starting point? The starting point is an Hamiltonian, which is a function of your phase space. So for simplicity, I'm just going to consider like one-dimensional or two-dimensional phase space, but this means that I have one. So I'm just going to write in terms of Q or X and P, the phase space variable. So this is the starting point. And usually the kind of question you have is, so you have a quantity that is going to be a polynomial of the phase space variable, and you want to have the equation of motion. And the equation of motion of that variable are given by the Hamiltonian equation. Which give you, so if f is a phase space function, you get where here we have this Poisson bracket, okay? And of course, you need to, if you want to solve explicitly this equation, you need to evaluate this Poisson bracket explicitly. So usually you're going to use a representation of this Poisson bracket. And it's what you had in the tutorial yesterday. The way you do that usually is using the definition in terms of derivative, okay? And so that's why, but this representation is not going to hold at the quantum level, okay? So this is valid. The representation in terms of derivative is valid at the classical level, but is not going to hold at the quantum level. So we want to find characteristic of this Poisson bracket that holds also at the quantum level. And again, it's going to another level of abstraction, okay? So here you're representing your, so it's very useful when you want to do complicated calculation. It's much more easier usually and much faster to use this in terms of derivation. Whereas to use what we're going to write now, which is a more axiomatic way of defining this Poisson bracket. So that's why for the homework 1, yesterday I asked you to think about another way of defining, an axiomatic way of defining this Poisson bracket. And most of you were almost there, or at least you understood the question, meaning that you knew what I was asking. So for most of you, you had almost everything, few details were missing, okay? So let's do that again together. Okay. So we can, instead of using the definition of terms of the derivative, we could also evaluate this using this following definition of. So instead of, we're going to use as a definition of the Poisson bracket, I'm going to use the following elements. So first, we need to specify that we have these are the canonical variable. And so I think one of you wrote as a comment in his answer that he was not sure that this was still going to go through at the quantum level, because at the quantum level, then you get another factor here. You get a I h bar, okay? But indeed, we're going to see that this is something necessary, but it's still the equivalent, okay? So we need that as a definition. And then now if we consider arbitrary function, so these are the phase space variable. And now for arbitrary function, f and g, which are function of the phase space. And again, everything here could be really generalized with many subindices, okay? So it could be xi and pi. It just is complicated notation sometimes, so I'm not going to do it. So then what were so most of you many of you were missing that, okay? And some of the property, but then, so what are the property you need here for abstract function? Yeah, antisymmetry. is going to be the first one. Then
linearity.
Yeah, linearity. So I'm going to decompose linearity in two different steps, like just when you multiply by, so this is just a number, a constant, and then say that here you have the addition. So this is part of the linearity. 1, 2, 3. So what else do you need?
Leibniz.
Yeah, Leibniz rule, okay, the product rule. Very good. So this one was also sometimes missing, and this is, in fact, a really important one. Plus, so G is H. Okay, so this is Leibniz rule or product rule, and we're still missing one.
Jacobi identity?
Yeah, the Jacobi identity. Okay, so plus okay, so now with this definition of this quite, so which can be, say, abstract and axiomatic way of defining the Poisson bracket, is going to be the same at the classical and quantum level. And just, so what all this set of property mean, okay? So here we consider polynomial of the phase space variables. And here mathematically, this means that this is a Poisson algebra, okay? So what is a Poisson algebra? A Poisson algebra is a vector space with two multiplication, okay? And we have one multiplication which is associative. So in our case, what is the multiplication here? It is a associative multiplication. So you have, well, maybe let me give you the second multiplication. What we call the second multiplication is the Lie bracket itself. It can be seen as a multiplication, and this one is non-associative. And so maybe before going back to the first multiplication, how can you say that it's not associative? What is the property that translates that here? Yeah, okay, here the Jacobi identity exactly tells you that it's non-associative. And what is also the first multiplication? So you're dealing with function, okay? So it's going to be the pointwise multiplication between, so pointwise means that to define it, of course, you have to evaluate at a given point. Okay, so this a vector space with, and of course, so an algebra first is a vector space with a multiplication and an addition. So here you have the addition. And now you add the fact that it's Poisson algebra. So you add the second multiplication, which is a bracket. And that is non-associative. You also want that these two multiplications are kind of compatible. And the way you see that they are compatible, in a sense, is with the product rules here. Okay? You see that this is something telling you that you're looking, this here, you're looking at the pointwise. It's a kind of composition between, so the bracket, the Poisson bracket, and the pointwise product here, okay? Okay, good. Any question about that? So here, this is what is going to go. We're going to keep, in fact, most of that at the quantum level. And we see that for the Poisson bracket, we're going to get a new representation. I guess you can guess that it's going to give you the commutator. But so before going to the quantum level, I just want to finish the classical part by saying that, in fact, there are two kind of other assumptions that are done in classical mechanics. So for example, if you, let's say that we are in a very simple configuration, like here it's just the phase space xp, so meaning that maybe we're dealing just with a particle. But here, in fact, the other assumption we are doing is that usually we assume that the position and momentum measurements are compatible and come out as real number. And according to your everyday life experience, this is true, okay? You all have on your mobile phone a GPS, and your GPS can tell you very accurately at the same time your position and your velocity, okay? But we know that this is something we won't get at the quantum level, but this is a kind of assumption we have that is totally understandable with everyday life, in our everyday life. But so mathematically, all the fact that all this can be translated, okay? So the fact that the position and momenta can be accurately measured at the same time, simultaneously, is translated by the fact that this, so at a given time, are number valued function of time, okay? So this is and the fact that we are working with number valued function of time automatically gives you that this is an important property of this kind of function, is that it's commutative, okay? So we, of course, because of that, you of course have that this is it. And this is okay, so here in classically we make the assumption, so X measurement P measurement so yeah, they are like compatible or can be done and the result is that you get a real outcome. These are two kind of assumptions that you have. So the first fact is translated by this, and the second that it's a real outcome comes just from this relation. These are real functions. Okay, so now we have everything we need from classical mechanics, okay? So we review quickly the Hamiltonian formalism. And I added the two assumptions that are a bit hidden maybe, but that we are doing is that, and that implies that indeed we use this number value function as mathematical object and automatically they are commuting, okay? So of course, you can already guess that this is something we want to change, and it's related to the issue of the fact that we cannot measure both at the same time, okay? And indeed, so this comes from, in quantum mechanics, you know that you cannot know position and momentum simultaneously. This comes from, it's translated in maybe in the Heisenberg uncertainty principle. And so here, what do we need to change? So now let's move to any questions here. This was just the classical part. So now I'm going to go from classical to quantum, see what we're going to, which assumption we're not going to keep, because of course we need to change one of the assumptions. And then we're going to see that it's going to modify, and it's going to be a way, it's going to allow us to introduce the H, okay? Because the idea is from the beginning, we know that we want to introduce the H somewhere. Okay, so if no question now, let's just go from, so this is what I call number 3. So it's from okay, so in quantum mechanics, we have the which tell you that the more precisely the position of a particle is known, the less precisely its momentum can be determined, and vice versa. And this is known through the well-known equation, which give you something like this. So we're going to come back on the H-bar. So now, how can the interference of measurement devices can be mathematically expressed as property of X and P? Okay, so here we said that classically, X of t and P of t are just number-valued outcomes of the position and momentum measurement as function of time. Okay, so at the quantum level, this function will not be anymore number-valued. Okay, and we're going to generalize that to linear map. Okay, or to map if you want. In fact, everything can be seen as a map. Even a number, you can just say that a number, if you want, you can describe a number as a map. It's just so this means that now we're going to what we want to say. So this is this assumption that I'm going to remove. So what we're going to say is that X and P are not number valued. And we're going to see them as map, and so we are going to denote them now with a hat, okay, to make the distinction. And even, in fact, linear map. The linear map as the simplest one, and in fact, some work in quantum mechanics has been done to try to formulate quantum mechanics in terms of nonlinear maps, but there is no really, without really any success. Okay, so we're going to work with linear map, and then we're going to see that it's possible to modify now this commutation relation that we have here. To incorporate the H, okay? So if we just do this we change this assumption coming from the fact that measurement cannot be done precisely, simultaneously, then we forget about this number and we go to linear map, then we're going to see that now we're going to be able to modify, just with this assumption, we're going to be able to modify this commutation relation between this numbered value function and incorporate H, okay? So this is the idea. In such a way that, of course, now, sorry, this is not H, is a P. X and P as a map are not commutative anymore. Okay, so again, it was really realized by Dirac that all the Poisson bracket structures that we introduced above can be really kept, and that the Poisson algebra structure constraint is going to constrain, in fact, the form of the non-commutativity we're going to get between these two variables. So it's really come from the property of the Poisson bracket that you're going to get a kind of constraint on how these two now objects are going to be non-commutative. So here, what we're going to do is to look at Dirac's argument to see how this commutativity relation is going to be modified and get the Poisson bracket for x and t. Okay, the commutator for x and t. Sorry. So maybe let's go here. So what is the idea of? Oh, it doesn't work. We only have one blackboard here. Oh, no projector, one blackboard. Yeah, is getting. Okay, it's going to be. So let's. What is Dirac? Argument here. So we want to look at the following Poisson bracket, where now we assume that these are not anymore. These objects are not number-valued functions that are just map, and usually we don't expect that they are commuting. And we're going to see that looking at this Poisson bracket using the property of the Poisson bracket is going to constrain the way these objects are non-commuting. Okay? So there is two ways of decompose this Poisson bracket into simpler Poisson bracket. Okay, so let's do both in parallel, like then we can compare. Okay, so what is the first way? Oh, anyway, not the first way, it's the first way, because I don't know if you're going to choose the same one as me, but it's fine, I guess. So how would you decompose this into simpler? So using the property of the Poisson bracket, we want to decompose that into simpler Poisson bracket. Sorry? Leibniz rule, but I want two different ways. So of course you're using Leibniz rule, but you have this factor or this factor. So we can start by choosing, for example, doing this one, and the other way would be we start with this one, okay? So let's do first the first factor. So what do we get? So I'm using Leibniz rule. I'm going step by step just to make sure. A2, okay, and the other way would be to start. Sorry, A1, A2, B1, B2, and then so now I'm starting with the second, okay, second factor, so the second term. So I get something like A1, A2, B1, B2 plus B1.
I have one question.
Yeah.
Here we have, like, there it is stressed the order where we put like J and H from the left and from the right, but there it doesn't matter because they're functions.
Yeah, it's commuting.
Yeah, but here, where do you get the intuition that you have to put it on the right side or on the left side? From that Leibniz rule.
So the idea is that now you don't assume commutativity.
Yeah.
Okay.
Sure.
So this means that you're going to keep the order that you have to start with. Okay. So this is at least the first argument is that okay. So now we don't assume commutativity between these objects. So we do like it's already we choose an order here, so we keep the same order. Okay. Okay, so let's finish. So now we can, but you're right that it's not like, trivial. Yeah, especially that now I'm going to add, I want to expand this one. Right. And so where...
You can jump the B's, but it cannot jump the A1.
Yeah, but so the idea is here is that you consider like, okay, so you have something. So now I'm going to do what is between brackets, okay, and the A1 is here. But you're right that, yeah, I'm following what Diax did, and I guess this was his kind of intuition, and the result is, but yeah, I agree that maybe not every step are totally convincing. If you, because for us we know the result we want to go, so it's easy. But for him it was not the case first. It's quite amazing that he get there, but yeah. So let's just finish that and then compare. Plus B1, B2. So this is the first, expanding the first bracket. And then the second bracket will give me B1, A1, B2, plus A1, B2, and then A2. And so we can do the same here. And then we're going to compare and see what we get. So does anyone already seen this argument, or is it the first time? Okay, so at least something. So I'll let you check what I'm doing, because sometimes when you're on the blackboard, you write something, but you're a bit too close, so you don't really see. 2 plus B1, A1. Plus B1, A1, B2, A2. Okay. Okay, so I have everything. So now we can compare, and you can see that. So of course both should be equal. So we have the same term here is the same as this one. Then B1, yeah, this one is going to be the same as this one. And then I guess we have A1, B1, B1, A1, and then B2, A2, A2, B2. Okay, so here, if we're comparing both, what we get is that A1, B1, the bracket of that, times B2, A2 minus A2, B2 has to be equal to B1 minus and times the bracket between A2 and B2. Okay, so this is starting from this Poisson bracket, using, not assuming any commutation property between this object, and using the property of Poisson bracket, we end up with this relation. So what can we say now? So this has to be true for any A1, B1, A2, B2. So this is going to imply that any expression A, B in terms of X and P, okay, the position in my, have to certify something like this. Okay, so this is, so that if A and B are function of X and P, now we get K time where K here is a constant, okay, and where here you just recognize the commutator between A and B. Okay, so this is the way you would define and so if you remember at the axioms that you had in your tutorial yesterday that are the axiom for the canonical quantization, you remember that to go from starting, if you have a classical system describing the Hamiltonian formulation, then you know that the Poisson bracket is going to be translated into commutator multiplied by a constant. And the constant was given to you here. Of course, with this very short calculation, we don't get the constant yet. But we're going to see that we can still get at least that it has to be imaginary, an imaginary number, okay? And so we're going to see that in a moment. And then, of course, the exact value of this constant is a bit more tricky. I'm not sure how to get it. So I will give it to you at some point, but just let's see until where we can go. Okay. So this was, I guess, axiom 3 or something like this. So we almost get axiom 3, just starting from classical mechanics, modifying one assumption of classical mechanics, which is coming from what you know from experiments. Okay. And then okay, so let's see what we can get. So of course, I guess no, good. I haven't. So here were the two a bit hidden assumptions that are sometimes forbidden when we talk about classical mechanics. Is that so when you do measurement? So we already talked about the first one and we change it. Okay. So now it was that we get real outcome, and this was translated by this equation. Okay, so we're still going to keep the reality condition. So how is it going to translate now? So we still keep this. This is still a good assumption. When we do a measurement, we're going to get something, a real value, okay, a real number. So we keep the reality condition. So now that we are not talking anymore about number valued function, but about map or linear map. What is going to be the assumption for on X on this object and P? You should, I guess you know. So yeah, okay. And so because we keep this, we have the emission condition about an observable, so a physical quantity at the quantum level is going to be now an operator, a linear map, okay, which has to be Hermitian. Okay, so this was also part of one of the axioms, and this comes from the fact that we want to keep this reality condition. Okay, really good. So now let's try to, as I said, we can say a bit more about this constant. We're not going to be able to say that it's proportional to h bar, but we can say that it's an imaginary number. So for that, how do we show that? So if now this is valid for any map A and B, which are function of X and P. So let's just choose X and P, okay? So in the case of A equal X and B equal P, this now is the canonical commutator, okay, which was given somewhere, but I guess.
Nope.
No. Okay. I tried, but I guess it was there. Or maybe, but yeah, with only this number of blackboards, it's going to be tough to keep everything I need. But you remember, okay? It's easy. It's a commutation. The Poisson bracket between X and P just equal to 1. So this is just what I wanted to say. So now, if we use that, like equation up here. But for A, we get that x, let's write it explicitly, x p minus p x is equal to k. And now this is, of course, an operator, so it's going to be the identity operator. I don't know how you want to write it. Put as a notation. And so now what can we use? We can now apply the dagger, okay, to this equation, and this will give you that is equal to k. So we don't have done any assumption. And so what do you get? Comparing, so what is inside this bracket and here.
Minus k star.
Yeah, okay, very good. So which exactly means that k is imaginary. So maybe Jeremy, it's the time you can help me with English. I cannot say this word. Yeah, so imaginary. Yeah, it's okay. Now, when I say it slowly, it's I did it. Okay, so now, but I'm not going to repeat it. Okay, so you write it. I let you. So indeed, now we know that we have this I, H bar. Okay, just as a reminder, I guess you all know that, but. And so, yeah, just now we get the canonical commutation relation as expected. Okay, really good. So now, what else can be translated from the classical? So we started classical mechanics saying that the starting point is the Hamiltonian, and then usually what you're interested in is function on the phase space, polynomial of the phase space variables, and usually interested in the evolution of this function, and this is given by the Hamilton equation. So what is the equivalent of the Hamilton equation at the quantum level? It's, so if now I consider that H, my Hamiltonian, and F are just position, are just polynomial in the position and momenta, and which is going to depend only on time through their dependence on x and p for the moment, then how do you translate what do you get from the Hamilton? How is it called in the quantum level, the Hamilton equation?
It's Heisenberg.
Yeah, Heisenberg. Okay, so it's you had a hint here. Okay, so it's what we're going to solve in a minute. Yeah. Okay, so here this is valid if this function depends on time only through their dependence on x and p, and then the Hamilton equation just as transposed at the quantum level as just okay. Well, yeah, most of the time now I'm going to, so now we're going to be working on at the quantum level, so I'm going to forget about the hat notation, okay? But because we're done with classical, and of course this simplifies in the case of if f is just x or p, you directly get the well-known equation that you're used to. And the same for p, okay? And this equation also the so-called Heisenberg. Okay, very good. Any question now? So now, and in fact, so of course, at this stage, we don't have all the axioms that was introduced in the tutorial yesterday. Right now, we just have more or less the idea that we need to work. Physical quantity are going to be Hermitian operator. That the Poisson bracket now is going to be translated to a commutator multiplied by minus I divided by h bar. And we are still missing, right now we haven't talked about vector or anything. But before going through, I just want to see, let's work a bit on this Heisenberg equation and see what does it mean to solve a quantum problem, okay? So and for that, usually, right now, everything is abstract, okay? We started from this abstract definition of Poisson bracket. But usually, in practice, we're going to use a representation. So yesterday in the tutorial, you work with a matrix representation. So for today, we're just going to go back on that, use that, and see how we can use to really solve Heisenberg equation, and then maybe try to understand what does it mean how to relate our result to a measurement that is going to give you just a number. Okay, but so now it was part 4. Yeah, so I talked with some of you, and it seems that you would like to have a break during the 1 hour and a half. Is that the case? Or? Okay, so sorry to disappoint you. It's not going to be today. But I will start from tomorrow. Just because today I prefer to finish. I have something at the university at 1, so I prefer to finish 5 minutes early than take a break. But for the next lecture, I will try to give you a few minutes break during the 1 hour and a half. Okay, so now it's part 3. So we're going to be solving so a simple example. It's going to be the simplest example you can get, even not a simple. Using addition or prediction, which is still quite missing because we said that we want to get rid of the fact that x and p are number valued functions, but then how do we get a number? How do we relate a map to a number? Okay. So first, let's look at the matrix representation. You work with that in the tutorial. So now in quantum mechanics, we have seen that x of t and p of t are Hermitian linear map-valued function of time. And of course, an example of linear map is just matrices, okay? And so indeed, yesterday in the tutorial, you represented x and p using the infinite dimensional matrices A and A dagger. So now x and p. Well, now we're going to, so these are, and you show that it's not too possible to use finite dimensional matrices. So we have to go to infinite dimensional matrices. So this is what you showed during the tutorial yesterday. So which are A and A dagger. Of course, yesterday you worked with the harmonic oscillator, but this can be used in any problem for x and t, can be represented like this. So now if I use as a matrix, is going to be, so here I'm giving you a representation. This means that I have chosen a basis. The basis here is usually what we denote by this kind of n, where n now is an integer. So this is the basis I've chosen. And of course, it's not really easy to write the infinite dimensional matrices. So okay, so you got the idea. And then in tutorial, you define x of, let's say that it's at a given t0, that you can say that a plus a dagger and p and then you have shown yesterday that indeed they satisfied the canonical commutation relation that defined this way. They are obviously Hermitian. And this representation now can be used to explicitly solve Heisenberg equation. Okay, so of course, to solve this kind of equation, you need to choose a specific representation. So let's do that quickly because it's quite trivial. And I'm going to, as I said, I'm going to use a simple example. It's really going to be very simple. I just want to consider the free particle just because my point is not really so much about, because in fact, what you just have to do now is just to solve some differential equations that are really simple. So for a free particle, the Heisenberg equations are just going to be of this form. And okay, where we started, of course, from the Hamiltonian is just for free particle, just p squared over 2m. And so now we can easily use, so if x of t0, let's say we start the initial time t0, x of t and pt are defined this way, then we can easily solve, get x of any, for any t. We're going to use, are going to be of this form. T0 and concretely, if you really want to write that, you can really, you just substitute the A and A dagger and you just get really a matrix representation of this. So I let you as an exercise to check that indeed x of t and p of t are still Hermitian, that they still obey the canonical commutation relation and the equation of motion. And in fact, so let me just maybe give you, then you get this kind of object where you have really an explicit representation of your solution. Okay. I'm just going to write one coefficient or two. So again, it's infinite dimensional. So and then, okay, so I'm not going to write, we'll find anyway the solution in the lecture note, and it's quite trivial to get it yourself. And you get something, yeah, for P of t also. Okay, so now, of course, you need to check that indeed this object x of t and p of t are still Hermitian. They still satisfy the commutation relation, the canonical commutation relation, and are still solution of, indeed, solution of the equation of motion. And you will see in the tutorial tomorrow, you're going to prove that indeed the time evolution of any system is going to preserve the commutation relation and the hermiticity. Okay, so if you haven't done any mistake here, you should really, in 2 lines, you should be able to prove that indeed this is true in this specific case, and this is a general property. Okay. Okay, so the question now is, so this was very simple, but have we solved a quantum mechanical problem here? Yes, in the sense that we have found an explicit matrix valued function, x of t and p of t, that are still obeying the canonical commutation, that are Hermitian, and that satisfy the equation of motion, okay, at any t. And this is valid for any t. But in this specific example, x and t, x of t and p of t are given by these infinite dimensional matrices, okay? And you know that if you do any kind of measurement on the position and the momentum, you will end up with a number, okay? Now the question is, how do you get a number? And in fact, it's even more general. Any physical quantity in classical mechanics, you could consider the angular momentum a component of the angular momentum, or will be also, if you use this formalism, since it's a function of x and p at the classical level, at the quantum level, this will be also a matrix, infinite dimensional matrix, okay? So any kind of physical quantity you can think about if you use this representation are going to be written as infinite dimensional matrices. And any kind of measurements you're going to do are going to be number, okay? So how do you get a number? If I give you a matrix, and we know that here we're working with Hermitian matrices, how do you get a number? Okay, so the question here, maybe let's go over there, that I want to ask is, okay, so the question now is, it seems that we have now quantum equation of motion. We know we can represent our variable as matrices and we're able to solve all of that, but what about number? Prediction. So the first question is, how do you get a number if I give you an Hermitian matrix? So let's start from A. Hermitian, so how do you get a number? So as I told you, if you remember the axioms you had yesterday, what something is missing, the first axiom was telling you about Hilbert space, but more importantly, a vector in a Hilbert space. And up to now, we haven't talked about any kind of vector. So maybe we should introduce some vector. And if we introduce vector, we can indeed build some number from that. And you're going to recognize very soon this expression. So if I give you so let me just, well, of course, I'm summing over. Where here I'm using a vector. Of course, I could have started to give you this kind of number. So this is a number also. But is it a correct proposition? Why is it cannot be that we are interested in? So we are interested in prediction from measurement. It's going to be a number, but more importantly, it's going to be a real number. Okay? Is that something to be real? Okay, so because we want something real, we know that indeed this has to be something like this. And this should be really familiar with this expression, which become just now, if we use the Dirac notation, something like this, okay? And where now the vector is written as a ket. And from, if you remember the axiom yesterday, one of the axiom also, the last axiom was that the expectation value of A is going to be given by that up to normalization of your vector, okay? So this is, so if we don't normalize the vector, we have this number, so this is the expectation. And in fact, this is not, so you see that it's a cute way to introduce what was missing, the vector. But this is not, so starting from A Hermitian, this is not exactly the more general option to get a real number, okay? In fact, the more general option would be something this, where you consider the trace of an operator rho times A. This is also a real number if this operator rho is Hermitian. And in fact, you're going to see in the second half of the course with Aggie that it's much more interesting to work with density metrics. So this is what you're going to call, because you can treat, in fact, what I wrote here is just a simplification where you would write rho as, meaning that you're considering pure state, okay? But we're going to see that more generally, not every system can be described in terms of a pure state, and then you will have to work with the density matrix. But even already with pure state, in fact, it could be useful to already consider density matrix. I'm not going to do that now, just because, for example, you know that if you consider these two vectors, so this is just a short comment, okay? These two vectors, for example, are going to give you the same expectation value, okay? But now if you go to here, you get the same expectation value. So physically, you cannot really distinguish between them. And there is, you don't have any more this issue if now you go to the density matrix, where indeed this is equal to that, okay? This is also a good motivation to consider density matrices even in simple cases where you work with a pure state, okay? So this was just a comment that, in fact, the expectation value in the more general framework would be, can be expressed this way, where now rho is a density matrix. So a density matrix is a Hermitian operator. It's also positive, and usually you add that the trace of rho is 1, which is equivalent to say that your vector here is normalized. I haven't chosen yet, okay? And just also, so this can also come from the fact, if you start from that, you want to get a real number, okay? This is the more general expression that you can get, okay? Okay, so, but it's working now. Ah, no, it's this one which is not working.
It's working.
Okay, only this one is, okay. Now I got it. So I did that before. Okay, so let's go back here. Okay, any question? So before going back to the axioms that was given in the tutorial yesterday, I just want to now just finished for today with going back to the definition of a Hilbert space in particular. So just maybe before doing that, a comment on the homework part. So you have seen that in the homework, I also asked you if you had any questions or comments. So this is really useful. So don't worry. Yeah, maybe I'm not going to answer all your questions the lecture right after. Sometimes I will answer the question. I will wait to answer to your question because I know that I'm going to talk about that in a future lecture, or if it's not the case, I will take some time during one of the tutorials to answer all the questions that are left. Okay, so it's really good that if you have questions, you ask them and don't feel that I'm not reading them. I'm reading your question. So in particular, from what you did yesterday, so there was one question on Hilbert space and this definition of complete in the norm and what does it mean and why we need that. Okay, so since we have 15 minutes left, I'm not going to rewrite the axioms now and finish. I'm just going to take the time to talk a bit about the Hilbert space. Okay. So this is going to be the last part. So let's go from 4 to 6, but it's 5. Okay. Especially that so now we have, so what I just done before is a way to kind of relate a matrix valued object to a real valued measurement by introducing a vector, okay? And so as I already mentioned yesterday, prediction of expectation value are only going to depend on the abstract operator and abstract vector, okay? The representation you're using, it's not important. So really what is important is the abstract structure behind all that. And so in quantum theory, we're working with the notion of Hilbert space. Okay, so let's, Hilbert space is going to be a complex vector space, but a bit more than that. So the first definition I want to give you is a complex vector space which is going to be equipped with a scalar product is called unitary vector space. There are different names. So I'm going to give all of them like this, depending on which book you consider. You may find a different name, but they're all equivalent. Inner product space, or also Hilbert space. And indeed, it's not quite yet an Hilbert space. So here it's just a complex vector space with a scalar product is what we call a pre-Hilbert space, okay? And so any finite dimensional inner product, or the way you want to call them, is going to be a Hilbert space. However, in quantum mechanics, we have seen, especially here, we work with X and P. So we need to work with infinite dimensional inner product space. And so we need to add a new condition, okay? So in the case, so here, let maybe just mention that. So in the case of, again, it's when everything is finite, everything is easy, okay? Finite dimensional. So if I consider a finite dimensional inner product space, this is automatically an Hilbert space. But so the issue is more for infinite dimensional. And indeed, so when it's infinite dimensional representation, this means that usually we're going to have to deal with this kind of, so in this case, we're going to have to deal with this kind of equation. Where here n can go from 1 to infinity. Okay? So we have sequence, we need to deal with sequences and that are infinite. Okay? And so there is a question of the convergence of this sequence. Okay? And so how do we say that a sequence of vector is going to converge? Okay, so maybe I can start with that. Maybe it's the best way to produce it. So the sequence. So here the issue is, so this is infinite, so is it about the conversion? Okay, so let's first define the convergence of a sequence. Okay, so a sequence of vector like converges. So usually we choose like another vector v. Okay, if and only if we say that the limit, when we consider this limit, and so this is just to define what I mean by convergence. And now a sequence is going to be called fundamental or a Cauchy sequence. Maybe you're more familiar with this terminology. If and only if the limit so if you took any two elements of this sequence and when n and m goes to infinity, then this is equal to 0.
That's a norm, or?
Yeah, it's going to be, it's defined with, yeah, maybe I'm,
I mean, your limit is defined.
yeah.
That's right.
Yeah. Yeah, so in fact, you can really see that as a kind of distance between vectors. And this is the point, okay? Because the idea, so what is now the definition of a Hilbert space? A Hilbert space is going to be, inner pre-Hilbert space or inner product space if all, so pre-Hilbert space is going to be called a Hilbert space if all its fundamental sequences, so all Cauchy sequences are going to converge, okay? And why do we want this is because then this, of course, is going to imply that all vector in a Hilbert space will have a finite length, okay? Because as you say, this is related, it's defined in terms of the norm. So this means the distance between any two vectors cannot be infinite, okay? So the norm of any vector cannot be infinite, okay? So this ensures you that if it's a Hilbert space, all your vectors have finite norms, okay? So maybe let's just write this. And And so really the idea of this Hilbert space is that if you have a pre-Hilbert space, you may need to add some elements to it, okay? And it's a bit the same idea if you start from rational number, okay? You can have sequences of rational number that are Cauchy sequences, but the limit is not going to be a rational number. So that's why you need to go to real number, okay? And it's the way you start from rational number to real number is by having this completion in the norm, okay? Meaning that all the limit of your Cauchy sequences has to belong to the set of elements you consider. So this is a bit similar here, okay? So the idea is that when you're dealing with infinite dimensional cases, your pre-Hilbert space is missing some elements, and the element you need to add is to make sure that all the limit of all the possible Cauchy sequences are part of this space, okay? So let's just write now the definition of a Hilbert space, and this will ensure you that now all vector of a Hilbert space will have a finite norm, okay? Which is something nice when you do some work in physics, okay? So Hilbert space is called all its fundamental frequencies converge. Okay, so this is the definition of and this is, so when it's a case, it's what we call to be complete in the norm. Okay, so sometimes you will read that Hilbert space is a complex vector space equipped with a scalar product and complete in the norm. Complete in the norm exactly means that all Cauchy sequences have their limit in the Hilbert space. Okay, so this is the same. So maybe this is related to the, maybe you can read sometimes something which is complete in the norm. Okay, and so really one consequence of that is that now all, and I'm going to conclude on that. Hilbert space have finite length. Okay, I'm going to, yeah, so of course, then you can, so in the slide yesterday, so the slides are posted on the wiki page, so if you want to review some of the definition or anything, so both the Rob's slides and my slides are both posted on the wiki page, so you can check the definition. So of course, here it's a Hilbert space. We have the notion of dual Hilbert space. This consists of all continuous linear functional, mapping element of the Hilbert space to a complex scalar. And then the Ritz theorem is giving you that you have a one-to-one correspondence between this dual Hilbert space and the Hilbert space, okay? Okay, so thanks for your attention.